So we're going to start chapter 1 in this video, and the bulk of chapter 1 is review from general chemistry. So in many instances I am going to go through the topics pretty quickly, sometimes just give you a list of terms, topics that I want you to go back and look at. The first part, however, is to just define organic. So organic chemistry. And our definition is just that it's going to be the study of carbon-based compounds. The name actually comes from organism. Back in the old-timey days, they thought that organic molecules had what was called a vital force, this kind of voodoo magic thing associated with them, and you couldn't actually convert inorganic to organic molecules and vice versa. We now know that that's not true. Vital force theory is a thing of the past. You can convert between them, so now just simply the study of carbon-based compounds. So some common atoms that we're going to see, of course, carbon. We're going to see quite a bit of hydrogen, oxygen. X is going to be our abbreviation for halogens. So remember, halogens were group 17, group 7A, so fluorine, fluorine, chlorine, bromine, and iodine. We're going to see some nitrogen, and then I'm going to add phosphorus and sulfur to the list. We're not going to see a lot of those this semester, but phosphorus and sulfur are common in organic compounds, particularly biological compounds. So common atoms. So we will see some other ones, but this is going to be the bulk of it. So essentially we're taking our entire periodic table and we're squeezing in a small little subset of atoms, right? All of these are nonmetals, and we'll review bonds here in a bit, but remember that bonds between a nonmetal and another nonmetal typically are covalent, right? We're going to be sharing electrons between them. So we will review that in a little bit. The first thing I want to do is just review parts of an atom itself. And this is just, I'm not going to test you on, how many protons does something have, but if I say how many protons does something have, or talk about it, I want you guys to know what I'm talking about. Sorry, that was messy. So what is, if we were to break down an atom into smaller particles, what can we break it down into? What are our subatomic particles? Yeah, hopefully you guys are thinking protons. And then we have neutrons. What's our third one? Yeah, electrons, good. So abbreviations. And then I'm going to make a little table out of this. So we'll have its electric charge, its relative mass, so comparing one to the other, and then its location in the atom in general. So a proton, what's my charge on a proton? Good, +1. Neutrons, electric charge. Yeah, 0, no charge. Electrons, -1, good job. Relative mass, I'll get us started on this one. So I'm going to say if a proton is about 1 AMU, right? Since we're doing relative, if I was to then compare a neutron to the mass of a proton, and a proton is about 1 atomic mass unit, what is the mass of my neutron? Yeah, they have similar mass, so also about 1. They're not exact, but they're very close to each other. If you were to actually round them to, I think, 2 digits after the decimal point, they round to the same number. So about 1 atomic mass unit for each. And then how about an electron? If we were to compare the mass of the electron to the mass of a proton and a neutron, what do we get? Yeah, it's really light, right? Negligible. I think it's about 1800, sometimes I write 2000, but it's much, much lighter than that of a neutron or a proton. It's not negligible. Some of you guys might have thought, or sorry, it is negligible. It's not zero. Some of you might have thought that. A lot of times in lower level classes, they'll say that electrons don't essentially have mass. They do have mass. It's just that it's so light in comparison to the protons and the neutrons that we just can generally ignore it. We would say it's negligible compared to the other two. But again, it does have mass, so be careful for that. We're not going to say zero there because it's not zero. Yeah, my nucleus. Neutrons. Yeah, also in the nucleus. And then electrons, you do not have to be specific. You can be super general here. So where are my electrons found? Yeah, some of you might say electron shells. You could get really specific and start talking about quantum numbers. All I really care right now is that it's outside of the nucleus. Right? It's not in the nucleus. So protons and neutrons in the nucleus, my electrons outside of the nucleus. A couple other terms I want us to remember. Atomic number. What was our atomic number? Yeah, our atomic number tells us the number of protons in the atom's nucleus. And these are on the periodic table. These are the whole sequential numbers on the periodic table. And we can pull a periodic table here in a minute and take a look. So our atomic numbers are on the periodic table. And very importantly, the number of protons, or its atomic number, because that represents the number of protons. So the number of protons in an atom's nucleus defines that atom as belonging to a particular element. So our example here, carbon, right? Carbon has an atomic number of 6, so carbon has 6 protons. If it didn't have 6 protons, it would not be carbon. Right? One of the common ways to write our symbols, if I want to talk about carbon-12, and we can talk more about what this number is in a little bit, oftentimes a 6 will be put down here. This 6, right, is representing my atomic number. And putting that 6 there and putting the C here is actually redundant. So I usually don't put the 6. I'll put the 12 because there's different isotopes, and if it matters which one we're talking about, I'll be specific. But if I'm putting the atomic symbol C for carbon down, it has to be 6, right? Carbon isn't carbon if it doesn't have 6 protons. If I had 7 protons, it would be nitrogen. If I had less protons, it's not carbon, right? It's boron if I had 5. So again, the number of protons, right? Let's make my highlighter bigger here. The number of protons in an atom's nucleus defines an atom as belonging to a particular element. We can change the number of neutrons, we end up with isotopes. We can change the number of electrons, we end up with ions. You change the number of protons, you change what it is. Mass number. My mass number is the number of protons plus the number of neutrons. And this is always going to be a whole number also, right? I'm not going to have fractions of protons or fractions of neutrons, so it's always going to be a whole number. These are not, I'm going to capitalize this here, on the periodic table. When we're learning parts of atoms in my 130 class, this is the biggest mistake that people make, is they'll look at the atomic mass on the periodic table and they'll write that down as the mass number. I can't have fractions of neutrons and protons. It's always going to be a whole number. It's a counting number. It's going to be exact. Remember, exact numbers come from counting or definition. Right? If you could like zoom in on the nucleus and count the number of particles there, that's what our mass number is representing. If I go up here, this here is my mass number. So this carbon has 6 protons because its atomic number is 6, because there's a C there, and I can look on the periodic table because I wrote a 6 where the atomic number goes. And then the mass number is 12. 12 minus 6 is also 6. So I have 6 neutrons in this atom of carbon. So I'm going to pull up a periodic table here. We don't have a specific periodic table for this class. Right, in 130, 150, 151, and 152, there was a specific one for that class. Here we don't have a specific class periodic table, so this is the one from 151. So one I usually use, and I'll post it on Canvas for you for those that want to print out a copy. But just kind of looking here, so these numbers here, the ones that go in order, so 1, 2, 3, 4, 5, 6, and so on, those are my atomic numbers. So if I was to look at aluminum, it has an atomic number of 13, so all atoms of aluminum have 13 protons. It doesn't matter if it's charged or what isotope I have, if it's aluminum, it has 13 protons. Right? There isn't a little microscopic Al floating around in space. There's a nucleus that has 13 positive charges in it. That's aluminum. So that's how we know what type of atom is, by the number of protons, number of positive charges in its nucleus. And then mass numbers, again, are not in the periodic table. Right? If I look at this is not my mass number. That is my atomic mass, and we can review that in a minute. But be really careful. I can't have 0.999 or 0.974 or 0.011 protons or neutrons. So those are not mass numbers. Mass numbers are whole numbers, remember. Oops. So atomic number and mass number. Atomic mass, I said I would review that real quick. Atomic mass is the other number on the periodic table, and this was a weighted average of all of an element's weighted average mass. Sorry, I forgot that one. That's an important what it is that we're measuring. We're measuring the mass. So weighted average mass of all of an element's naturally occurring isotopes. Which we should probably review also. I mentioned it a few minutes ago, but an isotope, these are atoms of the same element. So if they're atoms of the same element, they're going to have the same number of protons. Remember, if the number of protons were different, they're a different type of atom. They belong to a different element. So atoms in the same element, they have the same number of protons, but they have different mass numbers. So what that means is they have a different number of neutrons. So same number of protons, but a different number of neutrons. So we had carbon 12 as an example before. Carbon 13 would be an isotope of carbon. So I wrote the atomic symbol C down for both of them. So it has to have 6 protons, otherwise it wouldn't be a C. And then 12 minus 6 is 6, so this has 6 neutrons. 13 minus 6 is 7, so this has 7 neutrons. So those would be isotopes of each other. That would be their relationship, right? They have the same number of protons, so they're both carbon atoms, but they have a different number of neutrons, so they have a different mass number. Because they have a different number of particles in their nucleus, they're going to actually have different masses, right? If we were to weigh them, right, if we were to get their mass, they're going to be different. So if I was to take into account the percent abundance of carbon 12, carbon 13, and then there's also trace amounts of carbon 14. So if we were to take all of these into account and then weight that average, or get a weighted average, sorry, then we're going to have its atomic mass. So atomic mass is saying, okay, we have all of these in nature. They have different masses, but carbon-12 is way, way, way more abundant than the other two. So let's weight the average mass, and that's going to give us our atomic mass. If I go back to that periodic table, if I look at carbon here, its atomic mass, zoom in a little bit, is 12.011. So it's closest to 12 because carbon-12 is the most abundant isotope. It's a little bit bigger though because we do have carbon-13 and carbon-14 kind of in nature. So let's actually review parts of the periodic table also. Just like with atoms, I'm not likely to ask you a question or a test or a quiz about this, but if I say, you know, it's a noble gas or give me a metal, that sort of thing, you need to know where those are in the periodic table. So a real quick periodic table review. And I'll sketch a really ugly version of the periodic table here. We can go out to the one I have and mark that up also, but not everyone has a printed one in front of them, so we'll make this, which is not at all to scale. Sorry about how horrible it is. But let's do, we will come up to that. I want to talk about metals, non-metals, and then semi-metals. So we have metallic elements, right? Those that are metal, so they have all the properties that one would expect of a metal. So they're malleable, you can shape them and bend them into different forms. They tend to be good conductors of heat and electricity. We have non-metals, they tend to be brittle, not malleable, they don't conduct heat or electricity. And then semi-metals, also called metalloids. I don't usually use that term, but it is an acceptable term for semi-metals. And these have properties that are kind of exactly that, right? They're between that of a metal or a non-metal. So on our periodic table, there's a zigzag line that kind of goes through here. That's not proper placement. But our metals, these guys are going to be the left to the left. Of the zigzag line. That's what I call it anyway. It goes by many names. What's the exception to that? Yeah, hydrogen, except hydrogen. Hydrogen is a non-metal. Non-metal is to the right of the zigzag line. But includes hydrogen. Remember, hydrogen is a non-metal. And then my semi-metals, these actually share a border with the line. So these are along the zigzag line. But we have an exception here also. What's our exception? Yeah, aluminum. Aluminum is a metal. It's to the left of that line. It's along it, but it's to the left. So that's a metal because it's my exception. So if I go out and look, get rid of, I want my eraser here, get rid of some of the marks we made earlier. So this red line here is my zigzag line. So the atoms that are to the left of that, with the exception of hydrogen, hydrogen's a non-metal, are going to be metallic, right? Metal atoms. The ones to the right of that line are going to be non-metals, but you have to include hydrogen. And the ones that are along it, so they share a border, except for aluminum. Notice I skipped aluminum. These guys here are my semi-metals. So just be familiar if I say, you know, it's a metal, or, you know, be able to, if I give us an atom, know its properties in terms of metal, non-metal, or semi-metal. So I'm going to erase this here so when we come back it's nice and clean for us. Okay. So metals, nonmetals, and semimetals. So what are our horizontal rows called? Right? If I was to look at these guys, there's actually 2 in there. It's pretty messy. Okay, so this isn't to scale at all. What are these rows called? I feel the need to make this slightly better. Whoa, sorry guys, I didn't want to do that. Yeah, our rows, sorry, I was very distracting there. These guys are going to be called periods. So if I say things, you know, get smaller as you go across a period, we know what I'm talking about. What are my columns, my vertical columns? Yeah, those guys are groups. And then remember that atoms, or elements, probably the better way to say it, within a given group have similar properties. And that's why some of them have common names, right? And the common name that we're going to use most often in this class are halogens. I rarely say like a group 7 or 17. I generally call them halogens. So halogens being an example of a group. Noble gases, I use that one quite a bit too. I rarely use alkali metals or alkaline earth metals, but do you know halogens? It's one we're going to use a lot in this class. So going across, I have periods. Going down, I have groups. I did give us 2 naming systems here. If you don't remember that, remember there are 2 ways to name our groups, just straight up 1 through 18, or that AB method. So we go back to our periodic table here. If I look across the top, just straight up 1 through 18. So my halogens here are group 17, right? These would be part of group 10. Periods go across, they're just numbered 1 through 7. So this would be period 5 and so on. The other numbering system for my groups is, I just call it the AB method because I don't know what else it's like. It doesn't have a name, it's just an older method. But notice how it's giving a Roman numeral, and it doesn't have to be a Roman numeral. You could use regular numbers. But it's got an A's after those. So 1A, 2A, and then over here, right? 3A, 4A, 5A, 6A, 7A, and then 8A. And then these ones in the middle, these guys all have B's after them. So I just call it the AB method. I use this more commonly, particularly the A groups, which are our main groups, which we'll review here in a second. Because we can use that as a shortcut to figure out the number of valence electrons. So I use that a lot. So do you know the 2 numbering methods? So the other part, I just mentioned main groups. Let's divide up my periodic table here. So group 1 and 2, or 1A and 2A, and then group 13 through 18, or 3A through 8A, right? My A block, these guys are called main groups, or main group elements. So things in that A block. They're also called representative elements. I don't really use that term, but you may see it online or in a text. Trying to spell here. Always a struggle for me. Representative, sorry, that's what that says, elements. So my main groups, also known as representative elements, those are the ones that have the A's after them if you're using that AB numbering system. These ones in the middle here, these are my transition metals. And these ones down here are my inner transition metals. And again, it's just, if I say, well, magnesium's a transition metal, I want you to know what a transition metal is or where it is on the table. So again, just to be familiar with these terms, I'm not going to have a test question that says, give me 2 examples of an inner transition metal. Just if I use that term, know where they are. If we go back to that periodic table, let's get rid of some of this stuff. So marking this up again. These guys and these guys are my main groups. The B block are my transition metals. And then these ones down here are my inner transition metals. Right, and I remember that because they fit inner the transition metals. Right, if we go back and look at our period numbers, right? If you remember, periods are my rows. Notice how the 2 down here, my inner transition metals, don't have numbers, right? They're actually part of periods 6 and 7, if you guys don't remember that. So if you're following our numbers along, right, our atomic numbers, so here I get to 57, and then it jumps to 72, and it's like, whoa, wait a minute, what happened? There's an asterisk, and there's an asterisk, and here's number 58. So what happens when we get here, we actually go down to this. And then if we zoom over, I have 71, and then we go back up to 72. So if you were to like split open the periodic table there and expand it, then this first row of my inner transition metals actually fits in there. And that's how I remember the name, because they fit inner, right? They fit inside, they fit inner the transition metals. And then this is period 6, this is period 7, because these guys go down here. So this is part of period 6, this is part of period 7. The inner transition metals don't actually have group numbers. So they have period numbers, but not group numbers.